Hey, what's up, all you chemistry kids out there? It's time for Solutions Part 2. This lecture will go through the PowerPoint and we'll talk about a few things. Here are some of those things that we'll be talking about. Maybe. We're going to be looking, last time we talked about qualitative descriptions. This time we're going to talk about quantitative. That means like numerical stuff. So we're going to look at how much solute is in a given solution. So that's like how much stuff is actually there. Before we were just saying it's a little bit, it's a lot, like concentrated or dilute, or there's a lot, like a high mass or a high concentration. The three that we'll be looking at are called mass percent, parts per million, as well as molarity. Now, mass percent and parts per million, you may have heard of those somewhere in the past before. Mass percent is a little bit more prevalent than parts per million. Molarity is the one that we use in chemistry all the time. All right. So a couple things. Here's what we'll be talking about in the video. We're going to talk about these three ways of describing concentration. Then we're going to do a couple of sample problems. We'll do one of mass percent. We're not going to do any of percent of parts per million, because we don't need to know about that. I'm going to recommend that you go pause and go watch a video about molarity. And then I don't need these earbuds. I'm taking them out. You're going to do a few molarity problems after you figure out what molarity means, and then we'll talk about how you actually make the solution with those different molarities. Finally, I'll talk a little bit about what's coming next week, and yes, it's that ugly word, stoichiometry. There is going to be stoichiometry using solution reactions. So here we go. Mass percent's the first thing. Mass percent is just like it sounds. It is how much solute is in a given mass of the solution. So it's what percentage of the solution comes from the solute. So the way that we look at this is you're going to see this in real life in toothpaste. You see it in medicine. A lot of times toothpaste will be mass volume instead of mass percent. But ultimately it comes down to how many grams of solute divided by the total grams of the solution. That's going to give you a decimal. You multiply it by 100 to get a percentage. So again, how many grams of solute do you have? That's what you need to know first. Doesn't matter what the solute is. Doesn't matter how big the particles are, whether it's dissolved or not. We're just looking at how many grams of solute divided by the total grams of solution. And since we're looking for percentage, you have to multiply that by 100. All right. So here's the example that we want to look at. What is the mass percent of a solution that will be made if we add 22.5 grams of sodium chloride to 100 grams of water? So we're going to make some salt water. 22.5 grams isn't very much. It'd probably be like a teaspoon. It'd be a little bit more than you want to like drink. It would taste gross, especially in just 100 grams of water. That's 100 milliliters. For reference, that's about 1/3 of a can of soda. All right. So what do we know? We know that the mass of our solute, the salt, the sodium chloride, is 22.5 grams. The mass of the entire solution is what is next. Well, they didn't give me the whole mass of the entire solution. They gave me the mass of the solvent. So in order to come up with that, we have to add those two values together. So the total mass is 122.5 grams. So, oops. So to do the actual calculation, you would take the 22.5, divide it by 122.5. That gives me a decimal. I multiply it by 100, and I have a mass percentage of 18.4%. Mass percent, as long as you understand what's going on there, it's solute on top. Solvent is never in this at all. It's the total mass of the solution, and then you multiply by 100. All right? Oh, man, I keep hitting the little scroll button. Okay, here we go. Parts per million is a little bit different. Parts per million is for when there's things that are, again, it's just like it sounds. How many pieces out of 1 million pieces would there be? We use this usually if we have things that are percentage won't work. So you've got so little stuff that it's like, I don't really care. So the parts per million would be for, here's an example. If we had a bucket and we had 1 drop of food coloring, that would be about 1 part per million. And we symbolize that by ppm. If we put that same 1 drop of food coloring into a swimming pool, it'd be more like 1 part per billion. So I don't know if you remember the difference between millions and billions. In this COVID-19 era, where the government's giving lots and lots of money out. Billion is a million. That's pretty much what it comes down to. Oh, no, wait. I'm going to have to think about that. I'll come back to that in a minute. A million. Yeah, I can't do the math. We'll come back to this another time. So again, for parts per million, the percentage, like 1 part per million, is usually nothing. In fact, FDA stuff, they allow a certain amount of parts per million of things that you wouldn't want in your food to be allowed to be in your food. And we will just leave it at that. All right. We are not going to do any calculations of part per million, so you don't need to worry about the math on that. But you should recognize, like, if somebody said there's 50 parts per million or 430 parts per million, you should understand what that means. All right. So now the one that we care about the most, molarity. This is our friend. So molarity is the one that we use in chemistry to describe concentration. It tells us how much stuff is dissolved in a solution. Molarity is moles of solute. So notice before the other ones we had were grams. Now we're in moles of solute per liter, not of solvent, but of solution. That's kind of important. I want you guys to realize this. So this right here, this solution is not solvent. It's when you put the stuff together. So we've talked about this once before. If you were to take a scoop of sugar and add it into a completely full glass of water, what would happen? Hopefully you realize that by putting anything into that full glass of water, it would overflow. So the volume is going to change based on the solute going in. So anytime you see problems with this, you're going to see and hear things like enough water to make, or enough solvent to make a given volume of solution. It's never going to be, what's the volume when we add this many moles to this? Like, that's beyond what we can do. So it's always going to say something about in enough water. So at this point, here's the crazy thing. As we go through this, there's lots of ways to look at it. So it's moles per liter. It's capitalized with a capital M that's underlined. Sometimes in textbooks, you'll see an italicized capital M, but normally you're going to see it look something like this. It's a capital M with an underline. All right. So now, like I was saying, where this gets crazy, if we were in class, we would watch a video on this, but instead we have to go about this way. So it's moles of solute. What if I gave you grams? Yeah, you're going to have to convert from grams to moles. That means you need to know its chemical formula. And then what if I told you that we have 500 milliliters of water? Is that the total volume of the solution? It's not. So the liters of the solution. So after we've mixed it together, that's what we care about there. All right. So with molarity, you can make a solution of any concentration in any volume. So I can make 10 milliliters of whatever concentration I need, assuming that that solute will actually dissolve in the solvent. Right? I can make 500 liters, I can make 10 liters, I can make 1 liter. Typically in our classroom for all of the labs that we do, I make things in either 250 milliliters, 500 milliliters, or 1 liter. So hopefully you'll notice that this is always saying liters of solution. With molarity, we can make it in anything. But liters is key. Liters. I didn't mean to cross it out. Liters. Okay? If we were in class, we're going to watch a video. But we're not in class anymore. So I had to go and makeshift this. Right underneath this video in Moodle I've embedded the video. It's called the Molarity Song. And it is absolutely hilarious. To me, you guys are going to hate it. It was made back in the late 80s, early 90s, probably about the same time I was a high school sophomore. The kids that are in it look like they're high school sophomores or juniors. And Mr. Wood tries to do a really good job of explaining what's going on. So what I want you to do is pause this video now and go over and watch the Molarity Song video. It's about 20 minutes long. I definitely want you to watch the first, 5 or 6 minutes or so. And then if you want, you can kind of jump around from there, maybe even speed it up some. I was having issues with my DVD player, and so the volume and the sound, it's a little bit tinny, if you know what that means, the way that the sound went through. But again, it's an old video. You're just going to have to make do out of what it sounds like, all right? So pause right now, go over and watch that Molarity video. You'll be glad you did. All right, welcome back. So here we go. Molarity is moles per liter of solution. You take the grams, convert to moles, then divide by liters of solution. I would try to sing it, but I don't have my guitar, and plus I don't know how to play it anyway. And if I went over to the piano, I don't think I'd be able to pick it out. One of these days, maybe I'll figure it out. So this is the first verse. Molarity is moles per liter of solution. You take the grams, convert to moles, then divide by liters of solution. The second verse goes like this. Molarity is moles per liter of solution. To find the moles and convert to grams, you use molarity. Told you you're going to enjoy it. So again, they made orange juice, and then Mr. Wood has to make a solution for them to make elephant toothpaste. All of that being said, molarity is a very important concept. All right. So for molarity, we need to know what the solute is that we're using. We can't just say how many grams it is. It has to be in moles. So if you don't know the name or the formula, you got to come up with that first. So again, I've told you guys a long time ago, you're not allowed to forget anything we've done all year. So way long time ago, back at the beginning of school, I said you need to learn how to write formulas from names. Well, here we go again. There are some assignments in this that there's like 5 or 6 questions that it doesn't give you the chemical formula. It gives you the name, and you're going to have to come up with that. All right. So once you need, once you get that proper formula, then you can convert from grams to moles and moles to grams. So remember all that stuff? Yeah, it's still important. Those of you are like, oh my gosh, I never learned it. I'm going to go back and reopen all of those assignments again for all those of you who haven't finished them. And you need to remember, you need to know how to convert grams to moles and moles to grams. This is like the foundational information that you have to be able to do in chemistry. All right. So you still need it. Go in and do that. Figure out what you need to do. So here's your sample problem. All right. Oh, no, not a sample problem yet. I can't see my notes. The volume must be liters. You're going to see a lot of problems where they do not give you liters. They're going to give you milliliters. So the easiest thing to do is you're going to divide that milliliters by 1,000, and that will turn it into liters. So, for example, if we have 440 milliliters, that's 0.440 liters. If you have 375 milliliters, that's 0.375 liters. If you have 1,400 milliliters, that's 1.400 liters. If you have 65 milliliters, this is the one where it gets kind of confusing, because since we're dividing by 1,000, we're moving that decimal 3 places to the left. And notice it went 3 places left. It was 65, and the decimal point was here, right about there. And now we're moving it over there. So remember that you have to convert to liters. If you don't convert to liters, you're going to get the wrong answers. All right. So here we go. Find the molarity of a solution prepared by dissolving 25 grams of sodium hydroxide, NaOH, in enough water to make 750 milliliters. So with this information, what do we know? What do we need to know? So you have a grams has been given. We don't care about grams. We only care about moles. So you must convert grams to moles. Sodium hydroxide's molar mass is 40, exactly 40, 22.99 for sodium, 1.01 for hydrogen, and 16 for oxygen. That adds up to 40.00. All right. So we need to convert that. So we take our 25 grams divided by the 40 grams per mole, and we get 0.625 moles. That will be the molar mass of 40 grams, and we're going to take the mass we're given divided by 40 grams. There's your moles. Okay. So now what do we do with that? Well, molarity is moles per liter of solution. So you took the grams, converted to moles, and now we divide by liters. So we're going to take the 0.625 moles divided by 0.750 liters. Now notice that it's in liters, not milliliters. 750 milliliters is 0.750 liters. And when you divide, you get 0.833 molar. Right? So this solution would be a 0.833 molar solution. That's how we say it. That's the way that it's announced or talked about or pronounced. I don't know what word I'm looking for here. All right. So here's the other thing with molarity. What am I doing here? I skipped something. Something happened. Well, there's our conversion factor. So with molarity, the thing to remember is to get moles, like the other way around, Molarity is going to be volume on the bottom. So when you want to solve for moles from something else that's been given, I think I deleted the slide that had this problem on it. So here's the information we have. It would be, I don't know where my, hold on, let me see if I can find the slide. There it is. So somehow they got out of order. I must have moved things around. Sorry about that. So how many grams of copper 2 chloride would we need to dissolve in enough water in order to make 500 milliliters of a 0.37 molar solution? So what do we need to be able to do to solve for these things? You have to know the molarity, which we do. We need to, which is right here, okay? We need to know the volume, which we do, 500 milliliters, that's 0.5 liters. And now how do we get to moles from this? So to convert from molarity to moles, you multiply by the volume. That was this one that we had before that I messed up. Molarity is multiplied by volume to give you moles. Okay, so now if I have 0.185 moles, that's what I knew. Going back over here, we had this molarity and this volume. When you multiply those, you end up with 0.185 moles. But we wanted to know how many grams were required. So you notice the question, how many grams of CuCl2 are required? So now to do that, we have to multiply by the molar mass of copper 2 chloride. So I already did it for us. It's 134.45 grams. That's Cu, which is 63.55, plus 2 chlorines, which is 70.9, for a total of 134.45. And then when you do this, remember 1 mole would be on the bottom so that our units cancel, right? And we're left just with grams of CuCl2. Okay, so at this point, when we multiply, you get 24.9 grams required. So with molarity, what you're going to end up seeing is that there's 3 ways to look at these problems, depending on what you're trying to solve for. We can use the molarity equation to solve for any of the 3. We can solve for molarity, right? To solve for molarity, it's moles divided by liters. But what if I need to solve for the number of moles? Well, I just did that. Molarity times volume in liters will be equal to moles. But what if I need to know the volume? What if they said I have this many moles and I make this molarity? What's the volume? Well, to get volume, it's going to be the molarity divided by, moles divided by molarity. Because all we're doing is we're rearranging this equation, right? If we were to cross multiply, so remember molarity over 1. So if I cross multiply, liters times molarity equals moles, but then I need liters all by itself, so then I need to divide both sides by molarity. So moles divided by molarity will solve for the volume in liters. Here it is right here. Molarity is on the bottom, right here. Molarity on the bottom. The moles goes on the top. All right. So if I have 5 moles, but I'm making a 2 molar solution, that would be 2.5 liters of solution. All right. All right. So now, here's where we're going with this. When we're using molarity, you can't just make a solution more concentrated. The only thing we can do is dilute it. So when you add more solvent, it doesn't change the number of moles. All it's doing is adding more solvent, and the volume increases. So what we're doing is we're making this less concentrated. Again, you understand this concept from before. You know what dilute means, like when you put too much ice into a soda, it all melts and it becomes watered down. So when something is watered down, that's diluted. If you don't have enough solution, like when you have a soda, when you go to Carl's Jr. or whatever, and you push the little soda fountain and it comes out just syrup and then there's no water being mixed, that's too concentrated. So what we want to do is you want to add water to dilute things. So here's what happens. Notice that we're saying that the number of moles of solute does not change. Okay, the number of moles in my solution is not going to change. It's going to remain the same. So if you look at that molarity times volume equals moles, we can do that every time. All right, and here's what ends up happening. Multiplying molarity by volume tells us how many moles are in our solution. Goodness gracious. Then we need to determine the new volume after that. So if I know the molarity and the volume of what I have, but I need to turn it into a larger solution, then I just add more water, find out what the new volume is going to be, but I need to know how many moles we started with. So here's what that looks like. There's a mathematical equation we can use. And it's M1V1 equals M2V2. M1 is the initial molarity of the solution. V1 is the initial volume of the solution. M2 is the new molarity of what we're trying to make, and V2 is the new volume that we're trying to make. With these things, what ends up happening is we just do a little math problem, and it's super, well, I don't want to make it super simple algebra because I know how you guys have been on that. But all we have to do is rearrange this equation to solve for what we're looking for. So what will the new molarity become if we add 400 milliliters of water to 50 milliliters of a solution? All right. So we have this stuff. We know the molarity and the initial volume. So we have M1 and V1. Right? Here's V1. Here's M1. So what do we have to do? M1 times V1 equals M2 times V2. All right. M1 times V1, 1.75 times 50, is going to give us some number, and then we have to divide that by 450, and we get 0.194. Again, on my screen here, it's really hard to show that, but what we really did there, here, let's see if I can do this. We're going to erase those. Let's try again. Go back to our pen. If we divide both sides by 450 milliliters, right? And over here, if we were to take out that, if we divide this by 450 milliliters, that's a 4. What happens? Let's make that a better 4. There we go. What happens? On this side, milliliters cancel milliliters. Over here, the 450 milliliters cancels 450 milliliters. And then the only unit I have left is molarity, right? Isn't that what we were solving for? What is the new molarity? Okay, so 1.75 times 50 divided by 450, because I need 450 to go away. And then that's where our answer comes out of 0.194 molar solution. Okay, so dilution is going to be, you have a volume and a molarity, and you need to solve for either new molarity or new volume. Sometimes they'll say, here's what we started with. You'll hear the term stock solution. So back at school, in the back room, we have a whole bunch of solutions that have already been made. Those are called stock solutions. And I take those and I dilute them to make them whatever we need to be able to do a lab. All right. So when you see that term, when you take a stock solution, what do you have to do to dilute it to make it what you need it to be? That's what it's talking about.